Okay, so the next step is to prove that merge sort is correct, which doesn't seem very difficult at some level, but it's one of those things that are very tedious. So I'm going to do it in detail more because I want you to know how it's done than anything else, and also because merge sort is relatively simple, so it's easy to do. Real algorithms, this kind of analysis can get, this kind of proofs can get very tedious. So consider it as a, relatively toy example of how this is being done. So the question, of course, is how do you prove correctness of programs or algorithms if they're iterative or if they're recursive? So since recursion is really an algorithmic version of induction, then it's clear that recursive algorithm should be proved with induction. As for iterative algorithm, we want to use essentially invariants, right? So you have a loop, you prove some property that holds throughout the iteration of the algorithm, of the loop, and that's how you prove the correctness, of the algorithms. There are, of course, a complete field that study this kind of stuff. This is formal methods, and they try, of course, to do this kind of argumentation automatically with varying levels of success, because this is, of course, very difficult. Okay, so I rewrote merge, the merge sort, and also rewrote the merge. I changed the pseudocode a bit, just to make it a bit more readable, in my opinion. And our first step would be to prove that merge is correct. And once we prove that merge is correct, we will prove that merge sort, the recursive version, is correct. Okay? So what is the claim we want to make? And the claim is, again, a bit tedious. We assume that you give me the two arrays, the two parts of the arrays, the two ranges that you want to merge, and they are indeed given as sorted, and we would like to prove that merge indeed outputs the whole array now sorted. But now we are going to say that if we look on the pseudocode, we have this variable k. The variable k is to explain what this code does. We have the array b, k is equal to 1, it starts in the beginning of the array. We have those two portions of the array a, and essentially what we do, we copy, we have two pointers, if you want, into the array, and we copy those things into the array b and fill it up, right? That's what the code does, right? So maybe I should go through it. We start with k equal 1. Call as long as k is smaller or equal than n, namely we didn't fill the array completely. We check if I is larger than m. If I is larger than m, it means that since I is associated with the first portion, it means that we copied all the elements in the first part. If this happens, then we should copy from the second part. And indeed, if this is the case, we just set bk to be filled up with the next element of j, and we increase j by 1. I'm using C++ notation here to make life easier. The other condition where we want to do it is that j is smaller or equal than n, which means that the second part is not completely read yet, and the ith element is larger than the jth element, right? The current pointer, we have a pointer at location I and location j, and if the value at the jth location is smaller, we would like to copy this value into this array, right? Otherwise, we copy the ith location to the array. We do this until the array b is completely filled, and then we copy the array b into a, right? So this is this implementation of merge. It's similar to the previous one. I just erased it in this way because it's more compact. Okay, so now what the claim say? The claim says that if you give me the two initial arrays are sorted, and I'm assuming here all the input values are distinct to make things less tedious, then for any value of k refers to the value of in the program here, in the beginning of the loop, right, just here, if you want, just before we start the loop, the array B in the first k-1 entry contains the k-1 smallest element in the whole array A, and furthermore, this filled portion of B is sorted in increasing order, right? Okay. So let's prove it. And the proof is by induction. So the base of induction is k equal 1. When k equal 1, this is the first time the loop is entered, then k minus 1 is 0, right? In this case, the claim is empty, right? Because b1 to k minus 1 is b1 to 0, namely this is an empty array, and the claim holds in an empty way, so we don't have to worry about it. Now, the inductive hypothesis says the claim holds for all values of k that are smaller or equal than some parameter alpha. Okay? And now the inductive step is we need to prove that the claim holds for k equal alpha plus 1. Right? Of course, using the induction hypothesis. So let's do that. How do we do it? It's a bit counterintuitive. We look on the iteration with k equal to alpha here, where we start, right? So by assumption, we assume that the claim holds, right? So b1 to k minus 1 is sorted and contains the smallest element. And now we just have to go through the possible scenarios presented by the if. So let's do that. Either I is larger than m. If I is larger than m, that means that the first array was exhausted, and then we just need to copy all the values in the second array, and all the values in the second array that are left, they're definitely larger than the values entered so far because of the induction hypothesis. So then what the code does in this case, it's going to repeatedly perform essentially this copy command, and that's it. And as such, we just copied this suffix into the array B, and as such the claim would be true, right? Because we are just copying values that are bigger, and they are increasing because this whole portion is sorted. They are all larger than the value that already filled, so the claim is true. So this is easy but tedious. Same argumentation holds if j is larger than n, right? Because if j is larger than m, then notice that it must be that I is smaller than m, because if I is larger than m, then k is larger than n, and we would be outside the loop. So it must be, if j is larger than n, we are still inside the loop. It means that I is smaller than m, and then we will do this, and then we will do just this copying. Oops, now I'm confused. So let's try again. If j is larger than n, so this does not hold, right? And this does not hold, right? So this is 0. So as such, this would be copied, right? That's true. That's what should be done. Okay, so we are good. Okay, so both those cases are hold. So now we are left with the only situation where both I is smaller than m and j is smaller than n, which means that we are in this, we copied only those two portions. But then what happened is that, let's draw it maybe, we have the first portion of A, we have the second portion of A, we have I here, we have j here, right? And we have B1, we have B that we already filled, right? And now what happened is that B, the portion of B that we filled, is the k minus 1 smallest element that already were in the array. And now we know that the two portions of the array A that we are looking at, they are both sorted by assumption. That was the input. As such, the two smallest elements that are not copied to B yet are indeed in the ith entry and the jth entry. And this if here guarantees that indeed we copied the right values to the next entry in B. and as such, the values are going to be sorted for k plus 1, sorry, for alpha plus 1 in the end of this iteration, and the claim holds for k equal alpha plus 1. So that's the proof. Right. Okay, now I should say, by the way, something about proofs, right, and how to write proofs. I might have mentioned it earlier in the course, but it's not bad to mention it again. So what is a proof? A proof is a social process, right? I'm trying to convince you that a certain claim is correct, right? Now, so proofs, in this sense, when you write a proof, you should think about it in some sense as a dialogue, right? You're trying to convince somebody of some claim. Don't get fixated about the right wording, right? Are you using the right format to the right wording? Writing proof is not about filling forms. It's about convincing somebody of something. And in particular, it means that you should not, you should find the right level of detail, which is a very easy thing to say, but very hard personally, because, when you don't do it a lot, you're like, okay, do I need to go into more details, or is this enough detail? So I think that when you write a proof, you should think about your audience. Whenever you write, you should think about your audience. So think about your audience as somebody that is not stupid, right? It's somebody that know what you write, but they're a bit skeptical, right? They're a bit skeptical, and they're a bit adversarial, and maybe they are even going to play a bit dumb, right? So you need to kind of do it good enough to convince such a person, okay? So as I said, it's very hard to learn how to do it. Of course, you're going to see a lot of examples, but what I just did now. There are a lot of examples in the class notes. There are going to be examples in the discussion sections, etc., etc., etc. But at some level, you have to do it yourself, and my recommendation is just write it down and see whether you think this is good enough for your personal feeling. And the graders might disagree, but that's how you learn what's good and what's not, right? Okay, back to our purposes. So we just proved that this claim is correct, right? That there is this invariant on the loop of the merge, and that B indeed is being filled correctly. Now, we can now just take K to be equal n plus 1, namely, you can think about it as the final iteration before, the final iteration where we get out of the loop. And this would imply that B 1 to n is sorted and contain all the elements of A, and so on, right? Which imply readily that merge is correct. So that's the next claim. And we are done in the sense that we prove that merge is correct. Okay, the next step, of course, to prove that merge sort is correct, which we will do next.